I'll go back to what we talked on Monday. So we talk about the two gates you can do for solving the vector potential and scalar potential. So this, what we finish is the Lorenz gate, which is just because the general solution is in 610 and 611, so that kind of mixing phi and a in both equations, you want to decouple that. That the phi is as its own equation, a is its own equation. So that might make it solution easier. And one possibility is to choose this Lorenz gate that is divergence a plus 1 plus c squared. So 5. If you choose the Lorenz gate, then the equation becomes all equation depends on the same operation, the phi squared. Equals to. So it generalized from the Poisson equation, you add an extra term. So the operator has a Laplacian minus 1 over c squared second derivative. Right, and there's actually a name for this operator. It's very common. I think it's called the Lambert. Operator. I don't know whether you heard of it. And some people like, especially people doing relativity, they like define other symbols as a square instead of a triangle, an inward triangle into a square. I mean, obviously you define it. There's a different convention. I mean, you can reverse the two terms. This is positive, this is negative, and sometimes you multiply by c squared and all that. So you need to be a little careful with the square operator. The square, the square. So, without this phi, and then there's an a satisfying the similar equation, the same operator, but the right hand side is minus mu c. Again, similar to the magnetostatic extra term, right? But we don't talk. We'll talk about how you solve this this kind of differential equation right away. Hopefully later in this class, because we are kind of falling behind again. And so that's derived from 610 and 611 right away after you impose this one. Right, and we showed that last time that this is always possible. The solution always exists because you can always choose a gauge. If this is not satisfied, then you can choose a gauge to transform to a gauge transformation using the gauge lambda by solving lambda using the same kind of equation. And the right hand side is this one. So if this one is non-zero, you can choose a gauge, solve for a gauge, lambda, such that then you do a transformation from a phi to a pi phi pi. And in that equation, then this will satisfy, and then you have to do this too. Okay, this is an argument to show that the solution exists, but if you just simply, if you can find a solution satisfy this too. I mean, once you satisfy this too, and then quite easily you can see that this is satisfied because you can take the this operator on this two equations, like take the partial t on this one, right, with the 1 over c squared, and then take the divergence of this equation, and then add up, right, and then obviously then we will combine the two. So basically, this is well, this is if you don't want to write this, this is say this is a Lorenz case. That is here another function L, and you do this divergence of this plus 1 over c squared partial t of this, then you obviously you see that you have Laplacian L minus c squared L of c squared partial t squared. And the right-hand side is obviously 0 because you take this partial t of this one, so, and you have 1 over c squared. You take a partial t, right? So you have minus 1 over c squared, and 1 over epsilon 0 partial t. And the right-hand side for this one is just take the divergence of that, so you have mu c. Yeah, I took the bracket out. Right. And then you remember the c squared is 1 over epsilon 0 mu 0. So this becomes epsilon 0 mu 0. Cancel with epsilon 0 becomes a mu 0. Both terms have a mu 0. You take that out. And the rest is just the continuity equation. So that would be 0. So this, we satisfy a purely homogeneous, what we call wave equation with this D'Alembert operator. So as long as it's initially 0, then will always be 0. Okay, so so that's another way to show that once you solve it and then take care of the initial condition, make sure that the gate is this condition is satisfied, the Lorenz gate condition is satisfied, then it will always be satisfied because the right-hand side is homogeneous. Okay, so that is the Lorenz gate. Obviously, it also means that this two set has an inhomogeneous term, but you always can add homogeneous equation, or you can always set, even if this is 0, you can always add always change a gate that satisfies this homogeneous wave equation. So you can add wave solution to the lambda, do a gate transformation. All it does is just adding the homogeneous wave in this A and phi field, which present just electromagnetic field in free space, right? So it's just simple enough that this rho and J, they produce field, but then there are other field. These will give you inhomogeneous term, but the homogeneous term is just wave and all kinds of ways you can superimpose on the system. That's still a solution. Okay, so that actually a fairly simple mathematics. Always add homogeneous solution to inhomogeneous equation. Okay, so all right, so that's the first gauge, Lorenz gauge. The second one is divergence A is 0. Okay, but this one is okay, Lorenz gauge. We will hopefully talk about how to solve this operator a little later. The equation for that for the phi is actually simple. It's just the same Poisson equation, except that now rho can be a function of time also. Electrostatic required it. Well, rho is time independent, but for this Coulomb gauge, after you impose that, this is the same Poisson equation with the exception that the rho can be time dependent, but the solution should be the same. You're just doing a spatial derivative, so the Laplacian operator is still the same. The green function for it is still the same, so the solution is still the same, assuming that you have a localized charge density. Then the solution you can write it out. Yeah. Fine. 75 is just 1/4 pi epsilon 0. Remember all these things. T, it time depends on t. This is a function. Okay, that simple enough. The A equation becomes more complicated, and last time we said we want to rewrite it in a form that's more apparent that it doesn't depend on phi. Because right now, after you do the impose the Coulomb gauge, the equation actually is like that. So A, this is 6.24, same BLM, but then you have this extra term depends on phi. Okay, the way to kind of get rid of this phi, or at least make it not explicit, is use the continuity equation. But first, to use that first, you apply the mathematical theorem. So a vector can be expressed as two terms. One is what you call a transverse term. The other is longitudinal term. So you have the J longitudinal, JL injection notation. You can always do that, especially it's localized. When it's localized, we can write down the solution right. What it means is the longitudinal and transverse means that the longitudinal satisfy the curl of it is 0. So curl of L is 0, and the other one satisfies the divergence of it is 0. T. So the transverse field or J sub T is like a magnetostatic field. So divergence of it is 0. But the longitudinal is the other way around. It's curl of that is 0. But you can always decompose a vector in the addition of these two terms. That's mathematical theory. Have you learned about that in math? No, you haven't taken. You have taken undergraduate math. No, but you heard about that? This kind of thing? You have about it? Okay, good. I think there's a name that's called Helmholtz. I think it's Helmholtz. Okay. And then I don't want to spend too much time to write that. In my video of the previous class, I actually have a longer derivation, but I just want to now just follow Jackson. You can just write it down. You call it the mathematical theorem. You can always do that. And the solution, this is not restricted to current density, not restricted to a J field, but any field. You can. This is a mathematical form. Gradient of divergence. G x prime. I mean, for a mathematical, any arbitrary mathematical function, you don't have a t. This is just for us. You have a t. But for ordinary vector field, it's just prime. So that's the longitudinal term. And the transverse term, this is a function of x, and this operator is in x, so gradient on x. The integral is integration variable is x prime, and this gradient is x prime. So that you need to be a little careful. So the difference between x and x prime, t. Yeah, that's a t also.
So this is also the current, this current longitudinal.
They are part of the current, the same current density. Just decompose it. So any arbitrary vector field doesn't have to be current density. You can write it in longitudinal and in the transverse term, and then use these two formulas to calculate it. Once you calculate that, you add the two, you'll recover G. That's what the theorem is. I think. This is 4 pi curl. Yeah. And obviously, the theorem can be proved, but I don't want to spend time now to prove the theorem. Okay, so you have the formula to do that. So you have just separate J. So this J in the J's of T, J's of L and J's of T using these two formulas. Because the right hand side depends on J. For a given J, any given J, the divergence. Just the J itself and do this integral and do the gradient, and this is curl of curl. Okay, but that it will give you the right current after you do this add the two terms. This is divergence prime. This is inside the integral. This is outside the integral. This is x. This is a gradient in the variable x, or curl in the variable x. This is x minus x prime. And so you don't put this curl inside. So that's just the way it is solve the solution. Okay. All right, then the final step is this using this equation. So there's a gradient of positive t. You can take the positive t inside. Just consider this term. This term is pi epsilon 0. Yeah, and then take the positive t. Yeah, a c squared. And then you take the gradient. Right? But you take the positive inside. The positive rho t. That's just using the formula for the solution of this one. Then now you can use the continuity equation. The continuity equation, you remember that, right? So the continuity equation is just partial rho partial t plus j is t. Right? Now, once you do that, you substitute this continuity equation. This become minus divergence j, but then this is inside, this is of x prime, so this is divergent. Okay. And now you recognize that this term using the fact that c squared is 1 over epsilon 0 mu 0. So change that to mu 0 in the numerator. And you identify this is this one. This one has a minus sign, then you take the minus sign, become positive, and you have mu 0. So mu 0 over 4 pi gradient of this one. And then minus mu 0, exactly the same term. So the longitudinal part cancels. So basically, this is mu c j sub L. Right? And so j, part of the j sub L with the negative sign, you cancel with this one. So what is left is the transverse part. Okay. So after this, applying the mathematical theorem and the continuity equation, show that we basically get rid of the apparent dependence on phi. So the right hand side becomes just the transverse current. So there's another name for the gauge is transverse gauge, because it's later on in the radiation chapter, you learn that the radiation is still the transverse current. So that's also called the radiation current. Okay, so the equation for this is this one. So for A is this the Lambert operator on A equals minus mu c. So it's similar to this one, to the Lorenz, except it's not the full J. It's just the transverse part. Okay. All right. Then again, this gauge condition is also you can also show that the solution exists by the same argument. If it's initially not zero, then you can choose a gauge function lambda, solve for a gauge function lambda, and do a gauge transformation to a gauge such that this is satisfied. Or you can, by this equation, take the divergence of that. This becomes the lambda on divergence A. This becomes divergence A. This becomes divergence A. And this becomes divergence of J sub T, but divergence J sub T is just divergence J because divergence of this, you take a divergence of that. This is divergence. Divergence of T is 0. No, this the right hand side divergence of T is 0. So all this, the lambda on divergence of A is 0, right? And so that again the same argument here. If it's initially 0, then it will always be 0 because of we satisfy this homogeneous solution. The divergence A will satisfy the homogeneous equation by operators, the lambda operator on A, on divergence A. Right? So that will be 0 if you take care of it initially is 0. So once you solve the solution, make sure that initially is divergence A is 0, then you're fine. Okay.